I can't believe this, guys. We are on the topic of pulleys. This is the last topic that we have to do in forces, in dynamics. And the part that I can't believe is this is day 7 of school, and we, after this lesson is done, we are already at the same point in the semester where the COVID shutdown took place, the March 13th deadline. That's shocking to me. Absolutely shocking that that much time has passed so quickly. In only 7 days of school, we've covered 5 weeks. Now, mind you, that's without quizzes and without tests and without taking things up every single day. But still, it's absolutely crazy to me. All right, we've got one more topic to learn here today. And as you can see, there are no notes for this topic. It goes right into example 1 and example 2. So that's the good news. Like much of the work in grade 12, there's nothing new to learn here yet. It's application of grade 11. And let me show you how this topic works. So we're going to do questions where masses are no longer just sitting on a surface. They are slung over top of rotational pulleys. And we're always asked to solve for the same things when you do pulley questions in high school. Question A almost inevitably is, what's the acceleration? Like when the system is allowed to move, what will the acceleration of the entire system be? And the second question, part B, always asks, what's the force of tension in the rope, in the connection? We'll start with A, as that's the most obvious starting point. So you are going to have to figure out for each one of these pulley questions, when the pulley is allowed to move, at what rate will the pulley be accelerating? And here's how you do these questions. You start with a diagram of a pulley, and it's going to have at least 2 masses in it. And what you need to do before you do anything in the question is you need to label the forces. That's the main thing. Start with the diagram and make sure that you label the forces, because if you miss a force, you're going to not get the question right. Here's a question where if you read the description, there's a 5 kilogram mass over here. I'm going to write that right on there, and a 12 kilogram mass on this side. So let's start with the forces. Let's start with the 12 kilogram mass. It's a freely dangling mass that is not in contact with anything. So it is going to have a force of gravity straight down, and that's it. There is no friction, or there is no applied force. It's just dangling with gravity. On the other side of the pulley is a 5 kilogram mass, and same thing. This is a freely dangling mass. It's not in contact with anything, so there's no friction. It's not being lifted or it's not being dropped. This also has a force of gravity. Now things are going to get a little confusing, because in these questions you often have repeat forces. Like this question has 2 forces of gravity. So I would start to try and label them a little bit. Like I'm going to put a little 1 in the bottom corner and a little 2 in the bottom corner, just so we don't get these confused later on. So 2 forces of gravity. And then with pulleys, you have to remember that there's one more force that you have to add in. The rope itself has an internal force, a tightness. When the rope is pulled taut, because the system is allowed to move, the rope itself will have a little bit of a tightness in it. You label that as what's called a force of tension. And don't worry, it's not a new kind of force that's got a new formula, etc. But you have to label the force of tension. And in high school, the cliche way of doing it is at both ends of the rope. So the far end on one side and the far end on the other side. You're going to label the force of tension, and it always faces back toward the pulley. Okay, so here there's a force of tension, and here there's a force of tension. Now we don't have to label this a 1 and a 2, because it's actually the same force affecting both of these masses. So just to quickly recap, a force of gravity on one mass because it's dangling, a force of gravity on another, and that's it. Then I'm going to add in the force of tension at both ends of the rope facing backwards toward the pulley. Okay, so question A always asks, what's the acceleration of the system? And when it comes to dynamics questions, there's only one way to get an acceleration. Acceleration is net force divided by mass, the same way it was in all of yesterday's questions. So, just like a typical dynamics question, your job is to build the net force based on what you see in the diagram. So you're going to include all of these forces in one giant net force formula. But here's the trick, and I'm going to get a different color pen here, so give me a moment. I might as well wave my arms and keep the lights from going off. The trick here is, and this is very new and you have to be very careful, pulleys are weird objects because like several directions are happening at once. The 12 kilogram mass being slung over the left hand side, that's obviously the heaviest of these masses. So when this when this system is put into motion, the forward direction of this pulley, bear with me here, this is going to be a little weird, the forward direction of this pulley is going to look like this. Well, that's odd. I mean, forward was always to the right, or forward was always up. This is a weird situation. Forward is that direction there, a looping sort of direction over the top. So you want to build a net force formula, and any force that is in the forward direction is going to be positive, and any force that opposes that direction and is backwards, we're going to make it negative. So that's awfully strange, because you're sort of used to the idea that any force that points upwards, generally we call those positive, and any force that points to the right, generally we call those positive. Now you have to think things differently a little. It doesn't matter whether the actual force itself is up or down. It matters, is it in this direction? If it's in this direction, we're going to make it positive. If it's opposing that direction, we'll make it negative. And you have to have a sign convention like that to take care of this weird sort of multi-directional idea. So let's start at the very beginning down here. So we've got a force of gravity on mass number 1, and it's in the forward direction. So the first force I'm going to put in my formula, I'm going to put a positive sign in front of it to stress that it's in the forward direction. Force of gravity number 1 is in the forward direction. The next force is a force of tension, and it's opposing the positive direction. So I'm going to put a negative sign, force of tension. I'm going to continue back, I'm going to continue up the line and over the loop. There's another force of tension, and it's actually in the positive direction. So I'm going to write positive force of tension. And then finally at the very end of this line is another force of gravity, and this force of gravity is opposing the overall forward direction. So this is a negative force of gravity number 2. So that's it. I've taken all 4 forces and I've put them into the net force formula and carefully examined the direction on each one to make sure that that's going to work out. Now you have to divide by the mass, and the only thing you have to remember, which is a little bit different, is this mass is the mass of the whole system. So it's not mass number 1 or mass number 2, it's the mass of everything. The entire pulley system mass has to be used. So I'm actually going to write M total. Okay, so the force of tension, you're always going to have a force of tension that's positive and negative, and it's actually the same force of tension. So that's always going to cancel out. And you're going to come to the point where you say, why am I even bothering to write it? I know it's going to cancel out. I know I'm going to have a positive and a negative, and I'm not going to write it anymore. I'm just going to skip it. No, my suggestion is, if it's a force on the diagram, put that force into your net force formula so that when you look back at this, possibly in another year, you'll say each one of these forces was included, and it just so happens that that cancels out. But seeing it there and seeing it cancel out every time will remind you the sensibility of this, because there's nothing to memorize here. You're going to get to the point where every single pulley question is pretty much done the same way, no matter what it looks like. Okay, so in the next line, every one of these forces is going to have its own formula. So let's break that down. The very first force here is a force of gravity. And by the way, you won't see any formulas here that you haven't seen before. The first force of gravity is going to be mg. And I don't want to get it confused with anything else. So I'm going to make sure to keep that 1 in there, just to stress that it's mass number 1. The two forces of tension cancel out. And over here I've got a negative sign and another force of gravity. That's mg as well. But I'm carefully going to put a little 2 in here just to make sure that I keep track of which one's which. And on the bottom is the total mass. And it's important to write this word total in there every time, because if you just write m and you don't label them, you're going to look at this and think that it's work from yesterday, and you're going to say, oh, there's an m in every term, I can cancel them all out. If you cancel the m's, it'll be a disaster. It'll never work. They're not the same m's. And the m on the bottom is not even the same as any of the m's on top. So let's sub into all this. The very first mass was 12 kilograms. G is 9.8 meters per second squared. Mass number 2 over there on the right hand side is 5 kilograms. G is 9.8 meters per second squared. And the total mass of this system is 17 kilograms. You can have another line of work if you need to, if you want to work those forces out and see what the individual values of those forces is. That depends. It depends on whether you want to or not. I will. The first force comes out to 117.6 newtons. And the second force comes out to 49 newtons. And we're dividing that by 17 kilograms. I'm almost out of room, but there's only one more line left, and that's the final answer to this question. So 117.6 minus 49, and divide by 17. Same idea as yesterday. 4 point, I'm going to call this 0.4. Same idea as yesterday. This answer is not just a shot in the dark. There's a little bit of a limitation to this answer. It has to be between 0 and 9.8, because 9.8 meters per second squared is free fall. If there was no pulley system here at all and you just dropped one of these masses, the maximum acceleration you can have is 9.8 meters per second squared. And you can't exceed that. So that answer makes sense. Now comes the second part of the question. What will be the force of tension in the rope? This is really easy, but be very careful. In order to solve for the force of tension in the rope, you need to solve for Ft. But it cancels. So you can't solve for something that cancels out. So here's what you do in step B of these questions. You look at your diagram and you pick one mass, and only one mass. It doesn't matter which one. They'll both give the exact same answer. So pick one of these masses. I'm going to pick this one here. And what you're going to do is you're going to write a net force formula for just this mass. So forget the pulley system, forget everything else in the system, and pretend that that's a little mini question by itself. So here's what I'm going to write. The F net for just this mass, keeping the same sign convention as before. So I guess the one thing that I will keep from the pulley system is saying that the positive direction is anything that's up and over the top. So there's a positive force of gravity, number 1. And then opposing that, negative force of tension. And that's it, because I'm just writing a small formula for just this mass. The left-hand side of this formula, the F net, we're going to make a substitution for F net that you haven't seen for a while. Remember, F net, there is a formula for F net. F net equals MA. If you know what A is. And so there's the kicker here. You will know what acceleration is, because in part A you solve for the acceleration of the entire system. But it's a system that's all connected together. So if you solve that the acceleration of the entire pulley system is 4.04, every individual piece of this system has an acceleration of 4.04. You can't have one part of the system accelerating at a different value than another part of the system, because it's all tied together by a rope. So there's the key on how this works. We will replace the left-hand side of this formula, the F net, with MA. And at the same time, I'm going to substitute in for Fg, Fg1. That's mg. A force of gravity is always mg, and it's mass number 1. And I can't really break down the force of tension, so I'm just going to leave that as Ft. That's what we're solving for anyway. You have all these variables, but be careful. You're only writing a formula for just this mass. So all the m's that you see in this formula are only 12 kilograms. They're not 5 kilograms and they're not 17. I'm going to rearrange this because we're solving for force of tension. So with one quick jump over the equal sign here, force of tension will be mg minus ma. And it's the same mass. So you can either sub it in twice, or in this case, since it's a common multiple, I'm going to shorten things a little bit more before I sub in and take it out of the bracket, so I only have to write it once. So this mass is 12 kilograms, g is 9.8, and I'm going to subtract off the acceleration, 4.04. I should have put some units in here, but very poor format, I did not. Here, maybe I'll include meters per second squared just to say I did it. Okay, so on a calculator, 9.8 minus 4.04, I get my answer, and then multiply by 12. The tension in this rope comes out as 69.12 newtons. It may be right, it may not be right. You're not really going to know. There isn't a common sense range of answers for tension. It really can be anything. So you're not going to know whether you're right or wrong. But you just have to be confident that you did the calculation correctly, or you do have a backup plan if you have time. If this is on an assignment or something where you're not pressed for test time. Going back to the diagram, I said you could use either one of these masses. So what about this one? What if somebody just randomly chose the other mass instead? Well, nothing would change. Let me quickly do this one. And I know this is a huge mess. So I'm just going to squeeze it into the corner here. I'm going to write a net force formula, but it's only going to be for this 5 kilogram mass. Forget the rest of the pulley. And it's going to look a little different because of the setup of the arrows on this side of the diagram. So the F net for this, remember the sign convention, I'm still going to use that. So the force of tension is pointing in the positive direction. So I'll start by writing, I've got a positive force of tension and a negative force of gravity, number 2. I'm not going to divide by anything, divide by mass or anything like that, because I'm just writing a net force formula. The left-hand side of this formula is going to be ma, because we know the acceleration. So let me quickly isolate for force of tension. I'm going to take this negative force of gravity and bring it to the other side. So we're going to have ma on the left, bring negative over, it's going to become positive. And actually, while I'm bringing it over, I'm going to sub in my variables. Force of gravity is mg. And that will equal force of tension. Seems like the exact same formula as before, but if you take a look, there's a difference. The sign is different in the middle, so we will get a different answer, even though you're going to use a different mass, and it's going to feel like the answer is going to be different, but actually, it's not. I'll pull out a common factor, because we're only writing a formula for just this one mass. So both of those m's are the same. And then let's sub in the numbers and see what happens here. It's a 5 kilogram mass this time. The acceleration is 4.04 of the whole system, and g is 9.8 meters per second squared. That should equal force of tension. So on a calculator, and this is going to be very important, 4.04 plus 9.8 multiplied by 5 is a force of tension of 69 point, oops, I wrote it wrong, 69.2 newtons. Now, so these two answers should be the same. And you can see they're not. I mean, within reason they're the same. 69.12 or 69.2. Yes, yes. But I want to show you something. And this is really important for doing pulley questions. I want to show you something. The reason why they are not the same is because of this right here. Got to make a noise while I'm zooming in. Whoops. went too close. The reason why they are not the same is because when I did this in part A, let me show you on the calculator if I can get it into the same frame. All right, when I did this line in part A, 117.6 minus 49 divide by 17. The answer wasn't 4.04. Sorry, that was supposed to be in frame and it's not. The answer wasn't 4.04. The answer was this. This is one place in the curriculum where the more decimals that you write out, the more accurate your answer is going to be in part B. So instead of writing 4.04, what if I had written, no, this marker's too thick, so I'm going to have to write right beside it with a thinner one. What if I had instead written 4.03529 4? All right, I don't want to go too crazy. I don't want to write all the decimals, but let's say I didn't round it at all. So here we go. We're getting into that idea that if you don't round things at all, especially in multi-step questions where you're going to use that answer again, what will happen? So let me go down here. Let's go back to the first mass where I had written 4.04. What if instead I had written 4.035294? Well, guess what? The answer is not even 69.12. If I punch in 4.035294 and I do the work, add on 9.8, multiply by 12, I don't even get 69.12. I get 69.176. Going over to this other mass, same thing. If I didn't round, and I don't feel like I rounded. I mean, 4.04 doesn't feel like rounding. But had I instead not rounded at all and wrote 4.035294 and repeated that calculation. So I'm going to add on 9.8 and I'm going to multiply by 5. I get an answer of 69.176. It matches right down to the thousandth of a decimal place on both of those versions. You don't have to do 2 calculations to solve for the force of tension. You really need to do 1 and be confident that you're doing it right. But try to get into this idea that when you calculate the acceleration value in part A for pulleys, if you don't round it at all when you sub into part B, you'll get the most accurate answer possible. And then when your professors next year have you rounding your final answer to proper significant digits, you can be confident that yours is rounding to the exact significant digit answer that they're looking for. Okay, we are going to go on to example number 2, but I'm going to stop this video just in case something happens to it or if the battery runs out, and I'm going to start a new video. So you can take some time right now if you need to, or just click on the next video and continue on.